In two related videos, I've talked about uh, frequency response concepts for systems and shown how they can be derived from a model of the system, and shown an example for an analog voltmeter in particular that is studied in the lab. In some situations, we may want to go into the lab and maybe we don't have a model. We want to estimate the frequency response function using measurements. So that's what I'm going to talk about in this video. So experimentally determined frequency response function, again, either we may have a model, but we're trying to verify it, or we're trying to see how a system, maybe when we change certain parameters, what happens to the frequency response. So a lot of different reasons for doing this. I have a little figure here that illustrates a very common test. I mean, basically the idea of frequency response is you put in a sine wave and and measure the input and output and measure the amplitude ratio and the phase. That's illustrated here. I want to say two things. One is, often we talk about the linearity of the system, and certainly that's the case. What that says is that, well, if I put in a sinusoid with a certain frequency, what I get out is a sinusoid with that same frequency, with phase and amplitude change, depending on what your system's made of. You can always put a sine wave into a system that's not linear. You just won't. If you put in a sine wave, you're not necessarily going to get out just a sine wave. You might get different frequencies because of nonlinear type behavior in the system and so on. You can still do sinusoidal testing, and you can sometimes approximate nonlinear systems as linear. You might look at operation about a small point. About a point with small motion, and you could study a nonlinear system around different operating points, and they could behave linearly. The other thing is, and I'll refer to this in a couple of examples, SWEP. I'm going to talk about SWEP sign testing, but the other testing, you could actually put in, other types of inputs for doing this. And I may not talk too much about it, but I will mention that you don't have to just do sine SWEP testing. It's just one way of determining the frequency response. There's other ways to sort of interrogate the system to find out something about its frequency response. The other thing to keep in mind is, when you're making measurements, things, you have to have access to the input and the output signals. Sometimes, you may not be able to measure certain things. Sometimes phase is really challenging to measure, amplitude. And remember, these could be physical systems, so you may have sensors for some of these, you may not. So again, there's a bunch of caveats, and I always think about, noise and error and so on. Let me just show you a couple of examples that I like that we've talked about sensor bandwidth, accelerometers, and the frequency response insight into that kind of behavior. Obviously, there's actuators that can also have frequency response behavior. Where does it operate? What is the range of operation for that actuator? And then there's systems. So I like this example here. This is from a book on vibrational testing, and it's showing a little exciter here, which is a vibration exciter. So right here, there's something called an impedance head. So what that impedance head is measuring is it's measuring two things at that point, right? At this point right here, let me make it red so you can see it better. At this point right here, it's measuring. Imagine you got a system, and you're putting force and velocity both. Right, so what an impedance head measures is both of those. It's got a force sensor and it's got a accelerometer, and it can, so that you can interrogate, say, what is the force and velocity at that point that I'm putting in there, so that you can measure that. That's why it's called an impedance head. This is sort of a lathe mounting for a cutting tool. Maybe you're trying to look at, this is the cutting tool here, like what's its vibrational response, and look at what they've measured here. You can see they've also changed the mass on it and so on. So you can see that the frequency response, and it's kind of hard to see, but this is 100, 200, up to 1,000 hertz, really high frequency stuff. Compared to, for example, that analog meter that we're going to study in the lab, we're down at about 5 hertz is the highest frequency we're going. So when you're making measurements like this, you're using really high frequency measurements, accelerometers, and so on have to have high bandwidth, right? But look at what you're seeing. You're seeing peaks. You're seeing what's called anti-resonances and resonances, and it says something about two different cases. And so this is very common, complex structural system, and sometimes you just have to test this thing in order to really, and find out what is going on with its with what happens when I put a force in. What kind of response do I get? It might be too hard to build a model, right? So, or maybe you've built a model, in this case maybe with some FEA tools, and you want to verify it. So this is again where experimentally measuring these comes in very helpful. Here's another neat example from that same book on vibration and shock measurements. You might hang a big shaker and pound away at this rudder, and then you might have accelerometers at different points where you're measuring the response relative to where that force input is. Again, you're putting the power to get actuation, and then you're going to be having a bunch of force signals measurements. And again, you can look at frequency response between, say, the acceleration and the force, and you get transfer functions for each of those relationships at different points in order to study the response of that. So again, very common way to use frequency response functions. And one last little example here, I might show a couple of others. Oh, and by the way, like in here, it might be sinusoidal inputs, or it's very common also that you might actually use random inputs. And what happens with random inputs is that you might be able to get power across all frequencies, and then you have to use spectral analysis techniques in order to get these kinds of functions. The sinusoidal testing, you go frequency by frequency, right? And you get data at one frequency, and then the next one, and the next one, and you kind of march through the frequency range. By doing other kinds of signals, like with random and so on, you're using Fourier transforms, and you're doing spectral analysis and building transfer functions almost across all the frequency range of interest. All right, so this is a very, very mature field. There's a lot of different ways to do this. A lot of instrumentation has been around for a long time to do this kind of work for all kinds of structural systems, aircraft, ships, obviously, and so on. Another context is, this is one example I found in this book on control theory for physiological systems that I really like. And look, it's showing frequency response. This is a test where they took the eye pupil and they measured the area of the iris exposed to light. And so depending on the intensity, they looked at the area here. And so the transfer function is something like area over intensity, again, as a function of frequency, right? Pretty neat application. Oh, you can see here the area gain, and then there's phase shift, and then they measured data across frequency range of interest to understand how the human eye pupil is responding. Again, just to show you how this is used, and how would you build a model for this, right? So you would be very difficult to model this theoretically, so experimentally you can find out, oh, now I can understand what's the bandwidth for the response of the human eye to certain light intensity fluctuations. Neat application. So again, just I have one other example. One that we used that I remember doing in the lab. This was a motor putting in currents and just studying the change of a parameter. So here's a rotational inertia, a rigid shaft, and we measured frequency. And this was actually done by measuring, putting inputs of current that were random in nature, and rigid shaft getting the response omega over the current. And this is actually a first order response, because imagine this is a J, and the current, the motor doesn't have any, there's some resistance. So this is a first order system between the omega and the I. I'll show you the bond graphs in a second. Again, this is just a little extra example. So now if you decouple that, what if that shaft was kind of flexible? It introduces more dynamics, and you actually get a higher order system, right? And let me just show you, when you model these two systems with a bond graph, I'm going to scroll up here. You actually, here's the first case with a rigid shaft. When you introduce that flexibility, now you have inertia on the motor side and inertia on the load side. So it actually becomes a third order system, and that's what you actually see in the frequency response when you study it. So you can see that behavior, and either you can understand the how parameters influence the model, or you can actually try to characterize some of those parameters if you don't have them theoretically, right? Again, so the swept sign testing, just in review, and this is kind of what you can do for a lot of different systems, is you have something that you're trying to test. A circuit is super easy because you just have a function generator, easy to measure that. Maybe you have an oscilloscope, you can measure the output, measure the input, and so you can, the basic idea of swept sign testing is pretty straightforward. You turn the knob or push buttons on a function generator and sweep this frequency, measure these, however you're going to measure them. You could choose to measure peaks or RMS or other metrics of your signals. Where things get challenging can be when those physical signals are not easy to measure. So, in summary, again, transfer functions are, give you input-output relations that we can get frequency response functions from. We can estimate those experimentally using swept sign tests or other kinds of tests, right? Random, pulse, a lot of other things. If we have a theoretical transfer function, then we can compare that measured one to theoretical, to measure it in theoretical, and we can make judgments about the model. We can identify parameters. We can look at the influence of, we can adjust key parameters and look at that influence, measure it, and make sure it did what we expected it to do, and so on. So sometimes, again, we don't have some parameters and we're trying to estimate them from the frequency response function. That's something that we'll do in the lab. So I'm just going to show you in closing, when we go to the lab that we do with this analog meter, we think about the physical signals now that we have and what we've designed here. We can use a power supply to put in constant voltages to measure DC gain. In other words, put in a voltage here, Vs, and then measure, the theta, and then we can measure theta over V, right? Or we can put sinusoidal inputs here and then measure the theta. Think about now, and this is why we're using vision in this experiment, because right now because we can't put a sensor on this guy by putting a camera here, right? We can, do our object identification and measure the position at different points over time, or maybe just measure the peak thetas and build up, right, a frequency response, vary the input, measure that, make sure that we know what that input is. Sometimes we'll measure the input as well, just to make sure, if you don't know that you're controlling it very well. But look at what we have here. We know what the input is voltage. If we can control it well with the function generator, and then we're going to vary the frequency. When you think about your experiment design, and you have to know what range of frequency to use, what amplitude, and so on. And also note, one thing that we're not measuring here is phase. It's just too hard. We don't, because we're measuring, using vision and analysis with OpenCV, we're not sort of coordinating the measurement of theta at the same time as the input voltage. So we need to figure out, we would have to have a way where theta and voltage, in are being measured, simultaneously, because if you wanted to measure phase, you have to be able to look at those signals together. And as of yet, I don't have a real clean way of doing that right now that we've implemented. But it's good enough to get, right, magnitude data, and then if we can fit that to a model, then we know it's a second order in our case, and then we'll know what the phase looks like. Okay, so that's what you're going to be doing in lab, putting together all this concept, and then comparing the model that we built in a related video to what you measure, and you can at least identify for the analog meter the DC gain, because you can measure that from DC experiments, and from the Bode plot, experimental Bode plot, you can measure zeta and omega n. Okay, and that's all for this video.